Hello students, I hope you are all doing fine. In this lecture we are going to discuss about the convolution sum. So there are basically two methods for analyzing the behavior of a linear system for any given input. The first method involves the modeling of system with difference equations. So you have the difference equation of the system and then apply any input and then solve those difference equations directly or indirectly and find out the response of the system for any given input, right? And we are going to study this method in later lectures. In today's lecture, however, we are going to learn a method to find out the response of the system for any given input, which is called the convolution sum. In this method, the input is applied to the system and we have a system's mathematical model, and we actually convolute the input with the system's mathematical model and then compute the output. So before discussing the actual topic, let me spend few slides on resolution of DT signals into impulses. We have already discussed this topic during lecture number 2 when we were discussing about the impulse signal. And I told you, if you remember, that we can represent any discrete time signal in terms of impulses, series of impulses. So that is called with resolution of DT signal into impulses. And in convolution method, we actually first resolve the input signal in terms of impulses, and then we convolve the input signal with the system's mathematical model. So let us consider this signal x of n, right? And it has different values of samples at different values of n, and x of k is the value of this signal when n is equal to k, right? So we can represent this single sample as scale impulse, right? Like this one given in this equation, right? X of k of n is basically equal to impulse shifted by k samples, right? And as shown in this figure, right? So actually we can represent the entire signal as a sum of impulses scaled and shifted at different intervals, right? For example, this one is scaled and time advanced, as well as this one, and so on. This is what called the resolution of DT signal into. So when we multiply any discrete time signal with impulse, then for example x of k of n is x of n is multiplied with impulse which is shifted by k samples, then what we'll get? We'll get x of k only as a result, because impulse is 0 everywhere else, right? And this is also called shifting property. So x of n into x k of n would be equal to x of n into delta n minus k, or we can write this in this form, delta n minus k, where x of k is the scaling function, amplitude of this. So x of k is basically a constant. It represents the amplitude of the impulse, and this is the impulse function shifted by k samples. So in general, we can represent any signal in form of impulses like this one, x of n equal to k from minus infinity to infinity, x of k and delta n minus k. So x of k, let me remind you again, is the scaling function. It is a scalar which is multiplied with the impulse function. As I told you, any signal can be represented as summation of infinite number of scaled and shifted unit impulse sequences. The general equation for that is given here, and this is called the resolution or decomposition of signal into weighted sum of shifted unit sample sequences. Now let us consider this x of n, which is equal to 2403, and let us represent this signal in the form of impulses. Right. So resolve this sequence into sum of weighted and shifted unit sample sequences. So this sequence is basically non-zero at three intervals: n minus 1, n equal to 0, and n equal to 2. So we need three impulse functions: one time advance at this time n equal to minus 1, another at n equal to 0, and another at n equal to 2. So since the sequence x of n is non-zero for the time instant n equal to minus 1, 0, 2, we need three impulses at delays minus 1, 0, and 2. So we can now write down the equation: x of n equal to amplitude 2 multiplied with the impulse function with the time shift of plus 1, then another impulse function multiplied with 4 and occurring at n equal to 0, and another impulse function delayed by 2 units multiplied by 3. So this is the representation of this sequence in terms of impulse function. Now coming to the actual topic, let us consider a system whose function is represented by h. So h is basically the system operator, and let us apply this input, the input that we resolved in terms of impulses. Let us apply this input to a system h and see what happens. So pictorially, the system is represented by h, and x of n input is applied, and the response produced by the system is y of n, which can be written as in mathematically in this form: y of n equal to h is the function performed by the system, and the input is represented by this equation. Now, as I told you, this x of k is basically scalar. It is constant, right? It is a scaling function, so it can be taken out of the summation, and since the system is linear, we can call this scaling property, right? So using a scaling property, we can take this out, and then rest of the equation can be written in this form: y of n equal to summation of k minus infinity to infinity x of k and h of delta n minus k. Now this is basically impulse response of the system. H is the system, and this is impulse as input, right? So this entire expression is basically the impulse response of the system. H of delta n minus k is basically unit sample response or impulse response of the system, and let us represent the impulse response as h of n minus k. Right. So now we can rewrite this response of the system in this form: y of n equal to summation of k minus infinity to infinity x of k into h of n minus k. So this equation is called the convolution sum, and the convolution operation between two signals or between system and a signal is represented by a steric function, right? So when input is applied to a system, basically we are convoluting input with the system, right? So x of n would be multiplied with h of n, and it is represented by a steric sign, and it is equal to x of k into h of n minus k. Now if you want to compute the response of a system for any given input, apply input x of n and then convolute that input with h of n, you will get the response of the system. So this is one way to compute the response of the system, and then you can analyze the system's behavior from the response. The process of computing the convolution of x of n and h of n involves 4 steps basically, which are summarized in this equation, right? The first step would be folding of h of k. right? You can see h of k here is equal to n minus k, right? So first h of k is folded around k equal to 0. So first the from the equation of h of k, find out h of minus k, right? Time reversal, apply time reversal and find out what is h of minus k. Then next step, the after folding, obviously you have to apply time shifting property on h, because h is folded as well as shifted by n samples, right? So next step would be shifting of h of minus k by m units to obtain h of m minus k. Then obviously these two are multiplied together, h of k and h of n minus k are multiplied together. So multiply h of k by h of m minus k, and let's call it Vm. Then in the final step, sum all the values of product sequence Vm. Whatever the values you have got, whatever the samples you have got into Vm, sum all the values, right? Perform this function finally, right? Sum all the values, and sum of all the values is basically y of m, the response of the system at the value of n, given value of n. So it would be more clear when we'll solve any example. So let us solve the example to clarify these steps. So in this example, the h of n is given, which is basically the impulse response of a linear time invariant system, and it is equal to 1 to 1 minus 1, and we have to determine the response of the system to this signal x of n, which is equal to 1, 2, 3 and 1. So obviously we have to perform convolution x of n asterisk h of n. So the response of the system can be determined using this equation, y of n equal to x of n asterisk h of n equal to this convolution sum. Now the first step is to fold h of n. So h of n, or we can call it h of k because of the formula. So h of k is given by this sequence. It is equal to 2 when k is 0, it is equal to 1 when k is minus 1, it is equal to 1 when k is 1, and it is equal to minus 1 k when k is minus 2. Now let us fold it. Let us apply time reversal property. Instead of h of k, find out h of minus k. So when you fold it, you will get this signal h of minus k, right? So it is folded around k equal to 0. So now this sample would be at minus 2, this would be at minus 1, 0 would be at 0, and this would be at plus 1, right? So now the basically the h of k is folded around k equal to 0. So if we want to write down the sequence, so h of minus k would be simply minus 1, 1, 2 and 1. Now the next step is time shifting, right? So before shifting the signal, we want to find out the convolution when n equal to 0. So when n is 0, so first we'll compute the output when n equal to 0. It means no shifting, right? So the folded h of k would be multiplied with x of k, right? So now let us multiply h of minus k with x of k, right? So multiplication, as you know, would be the sample at 0 would be multiplied with sample at 0 of x of k. Similarly, sample at 1 of h of minus k would be multiplied with the sample at 1 of x of k, right? So multiply the samples which are synchronized time wise, and then find out the result, right? So for example, at minus 2, and in x of k at minus 2 we don't have any sample, it means there is 0. So when minus this would be multiplied with 0, it would be 0. Similarly 1 would be multiplied with 0, then 2 would be multiplied with 1, and 1, this one would be multiplied with 2, and similarly 3 and 1 would be multiplied with 0. So basically you will get 2 non-zero samples, and other than that all the samples would be 0. So you only get 2 non-zero samples, and which are product of this sample and this sample, which is 2, and this sample and this sample, which is 2 again, right? And other than that is 0, and let's call it is V naught of k, right? So V naught of k is basically product of x of k and h of minus k, right? And it is equal to 0, 2 to 0. Now the final step in computing the response y of 0 is sum all these values. So sum all the values of product sequence V naught of k, and the sum would be simply 4. Right. So y of 0 is equal to 4. Now we have to repeat all these steps for different value of n. Right. So let's now the value of n is equal to 1. So we are basically computing y of 1. So now in this case n is equal to 1. So h of minus k would be delayed by 1 unit and then multiplied with h of k. Right. So first now folded h of k would be shifted by 1 unit, right, to the right. So now the sample which is at 1 in h of minus k, it would be now at 2, and the sample which is at 0 would be at 1 in h of 1 minus k, and the sample which is at minus 1 would be at 0, and which is at minus 2 would be at minus 1. So each sample is basically shifted to the right by 1 unit, delayed by 1 unit, right? So after finding out h of 1 minus k, we will multiply h of 1 minus k with x of k, and then the product sequence will be determined, and from the product sequence you can determine y of 1. So now let us write down the sequence obtained from the shifting. The sequence which we got from the shifting is minus 1, this one, and 1 and 2 and 1. Now h of 1 minus k, this one would be multiplied with x of k. Again this sample at 0 would be multiplied with the sample at 0 of x of k, and similarly sample at 1 would be multiplied with sample at 1 of x of k, sample at 2 would be multiplied with the sample at 2 of x of k, and so on. So multiplying h of 1 minus k into x of k would give you v1 of k. So v1 of k would be simply 0, 1, 4, 3, right? Because minus 1 would be multiplied with 0 here, you will get 0. 1 would be multiplied with 1, you will get 1 here. 2 would be multiplied with 2, you will get 4 here, and 1 would be multiplied with 3, you will get 3 here, and this one would be multiplied by 0. You can write down 0 here, it doesn't matter. So you only get 3 non-zero samples, right? Which is 1 at 0, and 4 at 1, and 3 at 2. Right? Now the next step is to sum all these samples in the product sequence v1 of k. So when you sum all these samples together, you will get 8. So y1 is equal to 8. Similarly, find out the response at different value of n. For example, n equal to minus 1. So when n is equal to minus 1, then h of minus k would be shifted towards left by 1 unit, right? Mathematically you can write down in this form h of minus 1 minus k, and h of minus k is now shifted 1 unit towards left. So the sample which was at -2 would be shifted towards -3, and likewise all the samples would be shifted 1 unit towards left. Now next step is to multiply h of -1 minus k with x of k. Now h of -1 minus k would be multiplied with x of k, and exactly in the same manner we did for last two values of n. The sample at n equal to k equal to 0 would be multiplied with the sample k equal to 0 in x of k, right? So here after the multiplication you will get only one sample, because the samples in h of -1 minus k after 0 are 0, right? And samples in x of k before 0 are 0, right? So we have only one sample which are non-zero, otherwise we'll get 0 samples, right? So this is the result of the multiplication. We get 0 1 0, only one sample. And now sum all the values of the product sequence v minus 1 of k, and the sum would be equal to 1. So y of -1 is simply equal to, now let us choose another value of n, which is n equal to 2, and find out the response. So now x of k would be multiplied with h of 2 minus k. So h of minus k now would be shifted 2 units towards right. So this is h of minus k, and we'll shift h of minus k 2 units towards right. It means the sample at 1 would be now sample at 3. Sample at 0, which is 2, now would be at k equal to 2, right? And the sample at -2 would be sample at 0. Right? So when we shift h of minus k to 2 units towards right, or delay h of minus k by 2 units, we'll get this sequence -1 1 2 and 0. Now the next step after shifting is multiplication of h of 2 minus k with x of. So multiplication of h of 2 minus k and x of k would be done in the same way. The sample at 0 would be multiplied with the sample at 0 of x of k. Sample at 1 would be multiplied with sample at 1 of x of k, and likewise 2 would be multiplied with 3, and 1 would be multiplied with 1, right? So as a result you will get 4 non-zero samples. -1 multiplied by 1, which is -1, 1 multiplied by 2, which is 2, 2 multiplied by 3, which is 6, 1 multiplied by 1, which is 1. So v2 of k is equal to 0, -1, 2, 6 and 1. Now the next step is to sum all the values of the product sequence v2 of k, and when you sum all these values you will get 8. So y2 of k is equal to 8. Now let us choose the value of n is equal to -2, right? So now x of k would be multiplied with h of -2 minus k, right? So h of minus k would be shifted towards left by 2 units, or it would be time advanced by 2 units. So the samples which is at -2 would be at -4. Sample which is at -1 would be at -3, right? Like this. And the sample which is at 1 would be at -1. So the sequence that we will obtain after shifting h of minus k by -2 units, you will get this sequence: -1 1 2 1 and 0, right? Now the next step would be to multiply this sequence with x of k. Now the sequence h of -2 minus k would be multiplied with x of k. Now you can see that you will get 0 samples as a result of the product of h of -2 minus k and x of k, because all the non-zero samples of h of -2 minus k are occurring when k is negative, and all the non-zero samples of x of k are occurring when k is either 0 or positive, right? So the product would give you all the zeros, right? So this is the product sequence that we obtained after the multiplication, and this would happen when the value of n would be less than -1, right? So for all the values of n which are -2 or less than -2 will be the same result, right? You will get y of -2 or y of -3, y of -4, all the values would be 0. So further shift of h of -1 minus k to left will result in 0 product. Therefore y of n is basically 0 for n less than or equal to -2. Now let us find out the response of the system at n equal to 3. It means h of minus k now will be delayed by 3 units, right? So when h of minus k is delayed by 3 units, you will get this sequence. So the sample which is at 1 would be now at 4, sample which was at 0 would be now at 3, and so on, right? So the sequence that we obtain after delaying h of minus k by 3 units is this one: h of 3 minus k equal to 0, -1, 2, and 1. Now the next step is to multiply h of 3 minus k with x of k. Now h of 3 minus k would be multiplied with x of k. So the sample at k equal to 0 of h of 3 minus k would be multiplied with sample at 0 of x of k, right? So 0 would be multiplied with 1, will result in 0. -1 would be multiplied with 2, which is -2. 1 would be multiplied with 3, which is 3. 2 multiplied with 1 would be 2, and then 1 would be multiplied with 0, which is 0. So you get 3 non-zero samples as a result of the product of h of 3 minus k and x of k. And the product sequence v3 of k can be written as 0, this sample, and -2, 3, 2, and all 0. The samples of now product sequence v3 of k would be added together. So sum of all the samples would be -2 plus 3 plus 2, which is equal to 3. So y of 3 is equal to 3, and now we will compute the response of the system for another value of n. Now let us compute the response at n equal to 4. Now h of minus k would be delayed by 4 units, and after delaying the sequence you will get this sequence, right? So the sample at 1 would be delayed by 4 units. It means now sample at 1 would be at k equal to 5, and sample at 0 would be at k equal to 4, and likewise all the samples would be delayed by 4 units. And this is the sequence that you will obtain after delaying h of minus k by 4 units: 0, 0, -1, 2, and 1. So the next step is to multiply h of 4 minus k with x of k. Now h of 4 minus k would be multiplied with x of k. So the sample at k equal to 0 of h of 4 minus k, and this one would be multiplied with the sample of x of k when k equal to 0, which is this one, right? So 0 would be multiplied with 1, which is equal to 0. Then again this 0 would be multiplied with 2, which is equal to 0 again. -1 would be multiplied with 3, which results in -3, and 1 would be multiplied with 1, which results in 1, and this one would be multiplied with 0, which results in 0. So we get only 2 non-zero samples, so which is at k equal to 2 and k equal to 3. The next step is to add all the samples in the product sequence v4 of k, right? So summation of all the samples would be equal to -2. So y of 4 is equal to -2. Now let us delay h of minus k by 5 units, right? So delaying h of minus k by 5 units would result in this sequence, right? So the sample which is at 0 now would be at 5. and likewise all the samples would be delayed by 5 units, and as a result you will get this sequence h of 5 minus k equal to 0 0 0 minus 1 1 2 and 1. Now multiply uh, h of 5 minus k with x of k, right? So again the samples which are occurring at the same values of k would be multiplied together. So this sample would be multiplied with this sample and it would result in 0. This sample would be multiplied with this one, would result in 0. Similarly this sample would be multiplied with this one and would result in 0. And minus 1 would be multiplied with 1 and would result in minus 1, and all other samples would be 0. So we'll get only one non-zero sample, which is at k equal to 3. Now the next step is to sum all the values in the product sequence v5 of k, and the sum would be simply equal to minus 1. So y of 5 is equal to 1. Now we can see that if we further delay h of 5 minus k, we will get 0 in the product sequence. All the elements in the product sequence v6 of k would be 0, right? So therefore y of n is equal to 0 when n is greater than or equal to 6, or n is less than or equal to minus 2, right? So we get non-zero samples in the response when n is between minus 2 and these are the all 6 responses that we have obtained. At y minus 2 it is 0, and obviously at y minus 3, y minus 4, y minus 5 0 as well. So for y minus 1 to y 5 we have this response, and for y6 and y7 and so on it would be 0. So this is the response given in this figure, and this is the response sequence of which is the result of the convolution of x of n and h of n. Now the alternative way to solve this example is that we first place x of k here and then h of k, which are given in the question. Now here the sample occurring at k equal to 0 is represented by this bold number. Here this is the sample at k equal to 0, and this is the sample at k equal to 0. Now fold h of k. So folding of h of k would result in minus 1, 1, 2 and 1. So all the samples which are occurring at k equal to 0 are placed right under each other, so that we can easily multiply them together. And now if we want to compute y of 0, then multiply x of k with h of minus k, right? So multiplication of x of k with h of minus k, which is v naught of k, would be simply equal to 1 multiplied with 2 and 2 multiplied with 1, and other than that all the samples before this and after this would be 0, and y of 0 would be simply sum of 2 plus 2, which is equal to 4. And next step is, now let us find out the response of the system at n equal to minus 1 and n equal to 1. So for n equal to minus 1, h of minus k would be shifted 1 unit towards left, and like this. So h of minus k is shifted 1 unit towards left, and similarly for h of 1 minus k, when n is equal to 1, the h of minus k would be shifted 1 unit towards right. Now multiply x of k with h of minus 1k, and also multiply h of k with h of minus 1 minus k. So multiplication of h of x of k and h of minus 1 minus k would result in this sequence, and multiplication of x of k with h of 1 minus k would result in this sequence, and the result, the response of the system would be simply sum of all these samples, which is 1 in this case, and which is equal to 8 when n is equal to 1. So likewise you can carry on to multiply all the samples until you get non-zero results, right? And then you can write down all the values which are, so likewise you can compute the response of the system by placing all the shifted values of h of minus k and then multiply those values with x of k and compute the responses for different values of n. So in this particular example you can only compute the response of the system as long as n is between minus 2 and 6, because we know values other than between minus 2 and 6 the response is 0. So no need to spend time to calculate 0 samples. So the convolution operation is basically commutative. It means either you multiply x of k with the folded and shifted version of h of k, or you multiply folded and shifted version of x of k with h of k, you will get the same result, right? So it is irrelevant basically that which of the two sequences is folded and now this is shifted. The same example that we solved in previous slides, and now I am giving you this as a homework, that now fold and shift x of n instead of h of n and then find out the convolution, right? So you should get the same result. These are some exercise problems for you. You have to compute the convolution of x of n and h of n, and it is your choice whether you shift and fold x of n or h of n. It won't matter. Here is another example in which we are given the impulse response of the system given by this equation, h of n equal to a power n into u of n, where the magnitude of a is less than 1 and u of n is basically the unit step function. So this is basically exponential function, and when a is less than, magnitude of a is less than 1, then this is basically decreasing exponential. So the input that is applied to the system is unit step function. So we have to find out the unit step response of the system given by this impulse response, right? Now the values of h of n would be 0 when n is less than 0, because h of n is equal to a of n multiplied with u of n, and u of n is a unit step function, and unit step function values are 0 when n is less than 0. So h of n would be 0 when n is less than 0, and values of h of n when n is greater than or equal to 0 would be 1 plus a square plus a cube plus up to a power n. And this is the convolution sum we are going to use to compute the response of the system, right? So here we are going to shift and fold x of k instead of h of k. So x of k is basically unit step function, right? So it is written or represented graphically by this sequence, x of k equal to 1 1 1 for all the values of k which are equal to or greater than 0. Now folding of x of k would give you this result. Now all unit step is basically non-zero or equal to 1 when k is equal to or less than 0, and it is equal to 0 when k is greater than 0. Now we have to multiply this folded version of x of k with h of k. So h of k is basically decreasing exponential. Now multiplication of h of k and x of minus k would result in the product sequence v naught of k, right? So only there would be one non-zero sample, because the values of h of k before 0 are 0, and values of h of x of minus k are 0 after 0. So only non-zero value is at when k is equal to 0. So this 1 would be multiplied with 1, and you get 1 as a result of the multiplication of x of minus k and h of k. Similarly, when x of minus k is shifted or delayed by 1 unit and it is multiplied with h of k, you get two samples, one at k equal to 0, another at k equal to 1. So this 1 would be multiplied with 1, and this sample at k equal to 1 would be multiplied with sample at k equal to, which is a. So y of 1 is simply equal to 1 plus a. Likewise, the when x of minus k is shifted or delayed by 2 units, you'll get 3 samples as a result, right? 1 plus a square. So generally you'll get this kind of response sequence. Y of 0 would be equal to 1, y of 1 would be equal to 1 plus a, y of 2 would be equal to 1 plus a square, and so on, and y of n would be equal to 1 plus a square plus a cube up to a power n. So in general, we can write down the output for any value of n in this form: 1 plus a n plus 1 upon 1 minus a. Final value of the output sequence y of n can be calculated by using the final value theorem. Final value theorem means when n tends to infinity. Remember, the magnitude of a is less than 1. So final value theorem is y of infinity can be calculated as limit n tends to infinity and this function, the output sequence. Now evaluating the limit, you will get y of infinity equal to 1 upon 1 minus a, because a power infinity would be 0, because a is less than 1, and this is what you will get in response. The final value would be near to 1 upon 1 minus a. And these are some exercise problems. In these problems, you have to determine the convolution y of n of the following sequence graphically as well as analytically. Right? So solve those graphically and both analytically. And these are some other exercise problem for you. Compute and plot the convolution x of n into h of n and h of n into x of n for the pair of signals shown in the figure. So first, this one, x of n is given, h of n is given, and second one as well. Now the properties of convolution. The first is the commutative property. According to this property, if two signals or two systems or a signal in a system, for example x of n and h of n, are convoluted together to produce y of n, then it doesn't matter if you convolute x of n with h of n or you convolute h of n with x of n, the result would be same, and this is called the commutative property. Now the next property is the associative property. According to this property, if two systems are connected in cascade, for example h1 of n and h2 of n, and the input applied to these systems is x of n and the response produced is y of n, then we can actually simplify these two systems by convoluting h1 of n and h2 of n together. So we can replace these two systems by a single function h of n by convoluting the impulse response of this system, which is h1 of n, and the impulse response of this system, which is h2 of n. And the third property is the distributive property, and this is when systems are connected in parallel. So when two systems are connected in parallel, h1 of n and h2 of n, and this result would be basically the resultant function, impulse function of these systems would be simply sum of h1 of n and h2 of n. Now we are giving the impulse response of two systems connected in cascade. The impulse responses are given by these equations: h1 of n equal to 1 upon 2 power n into u of n, and h2 of n equal to 1 upon 4 power n into u of n, where u of n is the step function. So cascade of two systems can be determined by computing the convolution of both systems, h1 of k and h2 of n minus k. Right, so again let me tell you, it won't matter if you fold and shift h1 of k or you fold and shift h2 of k. In both ways you'll get the same result. So here h2 is folded and shifted and then multiplied with h1. Now h1 of n is given by this equation and h2 of n is given by this equation. Now convolution of h1 of n and h2 of n can be determined using this formula. In this formula we will substitute h1 of k as it is, and h2 of k is however folded and shifted. So we will substitute the folded and shifted version of h2 of k in this formula, and this product sequence is represented by v of n. So v of n is equal to h1 of k and folded and shifted version of h2 of k, which is h2 of n minus k. Now let us substitute the values. h1 of k would be simply substituted as it is, and h2 would be folded and shifted, right? So this would be 1 upon 4 power n minus k. Now because of the presence of this unit step function and this shifted unit step function, Vn of k would be non-zero for all the values of k equal to or greater than 0, and for all the values of n minus k equal to or greater than 0. Other than these values, the Vn of k would be 0. So simply we can rewrite this function in this form. Now the convolution sum can be written as h of n equal to k equal to 0 to infinity, not from minus infinity to infinity, but from 0 to infinity, 1 upon 2 power k and 1 upon 4 power n minus k. Simplifying it further by breaking 1 upon 4 into now we can rewrite this function in this form by taking 1 upon 4 out of the summation, 1 upon 4 power n out of the summation, and simplifying it further you will get 1 upon 4 power n and summation of k equal to 0 to n 2 power k. For n equal to 0, h of 0 would be 1 upon 4 power 0 and k equal to 0 to 0, which is equal to 2 power 0. So similarly we can compute the value of h of n for different values of n. For example, when n is equal to 1, h of 1 would be equal to 1 upon 4 power 1, k equal to 0 to 1 2 power k, and it can be written as 1 upon 4 multiplied by 2 power 0 plus 2 power 1. And similarly for n equal to 2, h of 2 would be 1 upon 4 square, k equal to 0 to 2, or it would be equal to 2 power 0 plus 2 power 1 plus 2 power 2, which is equal to 7. So in general we can write down the equation of h of n as 1 upon 4 power n into 2n plus 1 end of this lecture. And if you have any queries regarding this lecture, do let me know via my email address given on the first page, and I would suggest you, there are plenty of examples given in these slides. Try to solve these examples and have a good practice of these examples to understand the methodology of computing the convolution of the system. It is a very important topic, and we'll be using this topic frequently in our next lecture. So it is very important for you, for all of you to understand this topic and have a very good practice of this topic.